I want to set the stage a little bit by telling you about some of the motivations for this kind of area that I'm working in. So this project comes out of what's called trace methods in algebraic K-theory. And I'll say some more about what trace methods are momentarily, but the idea of trace methods is simple enough. So algebraic K-theory is an invariant of a ring that has a lot of applications across mathematics. So people are very interested in studying algebraic K-theory, but it's very difficult to compute K-theory directly. So the big idea behind trace methods is, well, K-theory is tough to compute, but we could try to approximate it. So in trace methods, what we try to do is we try to approximate algebraic K-theory by invariants, which are more computable. Okay, so how do we get started approximating algebraic K-theory? Well, let's say we have a ring. So we're going to be interested in the algebraic K-theory of a ring. And we could approximate this by another familiar invariant of rings, which is Hochschild homology. So we're going to try to approximate algebraic K-theory by mapping it to the Hochschild homology of the ring. And there is a map like this. It's called the Dennis trace that relates the algebraic K-theory of a ring to its Hochschild homology. Now I'm going to recall what Hochschild homology is, because this construction is actually going to be really essential to some of the things that I'm going to say later in the talk. So let's remember a little bit about Hochschild homology. So what is Hochschild homology? I have a ring, and I'm going to form what I'll call the cyclic bar construction on A. So this is going to be a simplicial object. Since it's simplicial, I have to tell you, what is it at each simplicial level? And then I also need to tell you the face and degeneracy maps. So for my cyclic bar construction at the qth level, I'm just going to take q plus 1 tensor copies of A. So what will that look like? Looks like this picture in the gray box on the left. I have at level 0, 1 copy of A, then 2 copies, then 3 copies, and so on. To define this simplicial object, I have to also tell you, what are the face and degeneracy maps relating these different simplicial levels. So let's start with the face maps. The ith face map, it's going to take as input a tensor like so. And what does it do? The ith face map just takes the ith coordinate and the I plus first coordinate and multiplies them together. So I'm going to get A0, tensor A1, AI plus 1, tensor AQ. And that makes sense as long as I is less than Q. It doesn't make sense for the last face map because there's nothing to the right of AQ to multiply it with. So the last face map is a bit different. It's going to take that last coordinate, wrap it around front, and then multiply. So I'm going to have AQ A0, tensor A1 through AQ minus 1 when I is equal to Q. Okay, and if I put these maps into my diagram, I have face maps like so. Okay, and for a simplicial object, I want to have degeneracy maps going in the opposite direction as well. And the degeneracy maps, they just insert a copy of the unit 1 after the ith coordinate. Okay, and so those degeneracy maps, they go in the opposite direction. Okay, so this is a simplicial object. This is called the cyclic bar construction. You can check that those maps, those DIs and SIs satisfy the simplicial identities. And interestingly, there's some additional structure in this simplicial object as well. So we also have what I'll call a cyclic operator. So this one is an operator within each level. So it's taking, my little typo, q plus 1 copies to q plus 1 copies. But it's taking on the qth level these q plus 1 copies of A to itself. But what it does is it takes the last coordinate and just wraps it around front. And so if we think about that cyclic operator a little bit, we notice that that actually generates a group action. It generates an action of this cyclic group of order q plus 1 at level q of my simplicial object. So I could put those group actions into my picture as well. Here I would get a C2 action, a C3 action, C4 action. Down here, it's just an action of the trivial group, and so on. Okay, so this is my cyclic bar construction. And from this, I claim that we can get a chain complex. So there is an associated chain complex, which I'll write as C dot A. And I have to tell you what is the boundary map in that chain complex. And so I claim that if you take the alternating sum of these face maps that we defined above, that does indeed square to 0. That's straightforward to check. And so we get a chain complex from that. And so what is the definition of Hochschild homology? The Hochschild homology, the Qth Hochschild homology of a ring A, is just the Qth homology of that chain complex. Now, the reason I defined it as this simplicial object is because it can be useful to think about this Hochschild homology definition in another way as well. The Dold-Kahn isomorphism tells us that the homology of that chain complex actually agrees with the homotopy groups of the geometric realization of this simplicial object, the cyclic bar construction. And so that characterization of the definition of Hochschild homology will be more useful when we want to start thinking about topological versions of these invariants. Okay, so this is the definition of Hochschild homology. Hochschild homology is a very classical invariant of rings. It's been around a long time. Before we move on from it, though, I want to make one sort of important note about this, is that I said it was a simplicial object, but it's actually better than that. So we had the face and degeneracy maps, but I had this cyclic operator as well that gave it additional structure. So this is actually what we call a cyclic object, meaning that it's simplicial, but it has a CQ+1 action on level Q generated by some maps, TQ. That was the map that rotated the last factor to the front. And that cyclic action satisfies some relations with respect to the face and degeneracy maps. So I wrote them down there. It's not so important exactly what the relations say right at this moment. But what's nice is that if we know that we have this, if we have a cyclic operator like this, and it satisfies these relations, we have the following fact from the theory of cyclic sets. So the geometric realization of a cyclic object has an S1 action. So we're supposed to think, we have these cyclic group actions at each level, and we're supposed to think that somehow in the realization, those assemble into an action of the circle. And that turns out to be very important in this trace method story. Okay, so that's Hochschild homology. And if we return to our trace methods, what were we doing? We were saying, okay, K-theory, we could approximate it by mapping to Hochschild homology. So there is a map like this. It's called the Dennis trace. There's good news and there's bad news with respect to the Dennis trace. So the idea of trace methods was supposed to be that K-theory is really hard to compute, and so let's approximate it by things that are more computable. Well, the good news is that this is definitely more computable. So Hochschild homology is, relatively speaking, very computable. We have a lot of tools from homological algebra that let us compute on that side. So that's the good news. The bad news is that this is not a very good approximation. And that's kind of to be expected. So I didn't talk about the definition of algebraic K-theory, but it's defined using homotopy theory. It's defined using topology. And Hochschild homology, if you think about that chain complex definition, was living purely in algebra. And so we somehow don't expect Hochschild homology to really capture everything that's happening in algebraic K-theory. It's like I would want to have a more topological version of Hochschild homology to be a better approximation. Okay, well, fortunately, there is such a thing. Böckstedt described this for us, or constructed topological Hochschild homology. And what is the idea? Well, the idea behind topological Hochschild homology is this. I want to take this construction I had in algebra, and I want to translate it to a more topological version. And we're going to use the same dictionary we always use in homotopy theory. This is one of the things we like to do, right, is take things from algebra and translate them to topology. And so a ring in algebra corresponds to a ring spectrum in topology. So a spectrum that has a multiplication in a unit. Where I had tensor products in algebra, I want to think about smash products of spectra. And, implicitly in my cyclic bar construction, I was always tensoring over the integers. Like I had this ground ring of the integers floating around. So one way to think about what happens when you translate from algebra to topology is that we change our ground ring to be, instead of the integers, the sphere spectrum. Now, once we've done that, actually the construction that we did a minute ago of Hochschild homology, it all makes sense, right? We can still define those space maps. We have a multiplication in our ring spectrum, so it still makes sense to talk about multiplying two coordinates. We have a unit, so it still makes sense to define the degeneracies. And so we can define a cyclic bar construction for R, just as we did in the algebraic case. And so what will that look like? Well, the picture will be similar, right? We have at each simplicial level, Q plus 1 smash copies of R, face and degeneracy maps. And again, we have this cyclic operator that brings the last factor to the front. So what is topological Hochschild homology? Well, one way to say what it is it's the geometric realization of the cyclic bar construction, where now my cyclic bar construction is in spectra. And one sort of notational note, one thing that can be confusing, is that, so the input of THH is naturally a ring spectrum, right? But I'm actually going to talk sometimes about topological Hochschild homology of a ring, like a ring from algebra. And so when we talk about that for an actual ring, A, when we write the topological Hochschild homology of A, that's just notation for the topological Hochschild homology of the Eilenberg-MacLane spectrum of A. So I can associate to that ring a ring spectrum. Okay, so this is topological Hochschild homology, and I have two kind of questions I want to talk about related to THH. The first one is, I said we were trying to understand K-theory. So the first question is, how does this relate to algebraic K-theory? I actually want to ask another question, which is, how does it relate to classical Hochschild homology? So this is a topological version, but is it related to my original theory of Hochschild homology that we had a moment ago? I'm going to start with the second question first. What is the relationship between THH and HH? So in this box, I've outlined one thing that we know about the relation between THH and HH. So, and this also gets at the question of how is THH related to algebraic K-theory? So the answer is there's a trace map from algebraic K-theory to topological Hochschild homology. This is just a topological version of that Dennis trace we had earlier to ordinary Hochschild homology. It's a better approximation to K-theory. So we're getting closer to K-theory as we move to this topological version. It actually factors the original Dennis trace. So this composite is the original Dennis trace to Hochschild homology. And so it factors as this trace map to THH. And then there's this second map we call linearization. So linearization is a map relating THH and HH. So a map relating the topological and the algebraic theories. So in the upper line there, I have what happens for a ring, but I want to make the point in the lower line that actually this all makes sense for a ring spectrum as well. You have a trace map from algebraic K-theory to THH. And then you have a linearization map, but now Hochschild homology, I need to feed it an actual ring, and the ring you feed it is pi naught of your ring spectrum. Okay, so a couple of notes about this. So the first is about this linearization map. So the linearization map, which is a map from the Q homotopy group of THH to the Hochschild homology of pi naught of r, this linearization map is an isomorphism in degree 0. So these two theories agree in degree 0. That's my first note, and that'll be relevant for us a bit later. And my second note that I want to make is that one relationship between Hochschild homology and topological Hochschild homology is that they're related via this linearization map. But there's another important relationship between the algebraic theory and the topological theory as well, which is that they're related via a spectral sequence. So Hochschild homology and the topological version are related via a spectral sequence, which is called the Bochstedt spectral sequence because it was constructed by Bochstedt. But they're related via the Bochstedt spectral sequence, which is an essential tool to computations of THH. So I just want to write down what the Bochstedt spectral sequence looks like, just so you can sort of see what kind of form this has. So the Bochstedt spectral sequence is a tool for computing the homology of THH. And the E2 term of the Bochstedt spectral sequence is ordinary Hochschild homology of the homology of R. So I'm going to claim in a minute that we really want to understand THH if we want to understand algebraic K-theory. And at the end of the day, when you look at the THH calculations that exist in the literature, like how have people calculated topological Hochschild homology, this is the primary computational tool, is the Bochstedt spectral sequence. And so if we want to understand topological Hochschild homology, we really also need to understand Hochschild homology. The relationship between these two theories is really crucial to the trace methods story. Okay, so I said we were trying to approximate K-theory. So let me just tell you very briefly how the rest of the trace methods story goes in very vaguely. So topological Hochschild homology is an S1 spectrum. The reason is just because it's the geometric realization of a cyclic object. So that gives us this S1 action on THH. It's in fact a particular kind of S1 spectrum called a cyclotomic spectrum, which is the topic of many other talks, but not something we're going to focus on today. But using that, you can define what's called topological cyclic homology. And this is the real approximation to K-theory that lets you do calculations. So there's a trace map from K-theory to topological cyclic homology. And my last bullet point is that is very vague. In good situations, this is close to an equivalence. Now, of course, there are very precise statements about this map and how close to an equivalence it is and what are the good situations. I put a few names here. Dundas, Goodwillie, McCarthy have some of the very famous theorems along those lines. But for this broad strokes overview, I just want to say that we're trying to compute topological cyclic homology. That's often the goal in trace methods. But it's defined from THH. So THH is an absolutely essential piece of that story. Okay, that was a super brief crash course in the trace methods story. And what I really want to tell you today is about a version of this trace methods story that has to do with what's called real algebraic K-theory and real topological Hochschild homology. Okay, so let me first start by saying a few things about what are these theories. So real algebraic K-theory is a relatively new theory due to Hesselholt and Madsen, and it's an equivariant refinement of algebraic K-theory. So it's a C2 equivariant refinement of K-theory. And the fixed points, the C2 fixed points of real algebraic K-theory recover another kind of K-theory, which is Karoubi's Hermitian K-theory. So there's been a lot of interest in recent years in understanding this equivariant refinement of K-theory. Let me tell you a little bit about what the input for this theory is. So with ordinary algebraic K-theory, our input was a ring or ring spectrum. With real algebraic K-theory, our input is going to be a ring or ring spectrum but now equipped with an anti-involution. So in other words, it's a ring that has this morphism, tau, that squares to the identity. So let me just remind you that anti-involution is capturing the notion that it's an anti-homomorphism. So if we're talking about, let's talk about actual rings for a second. An anti-involution, an anti-homomorphism will have the property that tau of xy is tau of y, tau of x. So the multiplication changes orders. The example you have, if you should maybe have in mind, or an example to have in mind, if you are thinking like, why do I want it to be an anti-homomorphism? The maybe example that I think helps make that, I don't know, convinces me anyway, that's something that you would want, is if you look at the group ring over the integers, and we get such an involution, by looking at the map that sends a group element to its inverse. But then if we think about, well, what is tau of GH? That's GH inverse, which is H inverse, G inverse, which is tau of H. Oh, I gave myself, ran out of room, hold on. Tau of H, tau of G. Okay, so so the input of these theories, this theory of real algebraic K-theory is one of these rings or ring spectra with an anti-involution. And there's a lot of interest in this, so one could ask a very natural question, which is, well, for algebraic K-theory, there was this whole story of trace methods, and that turned out to be really fruitful in understanding algebraic K-theory. There's been huge progress in K-theory over the last 30 years due to trace methods. And so one could ask, you know, I had this classical story of trace methods. Does that have an analog for real algebraic K-theory? And so in the classical trace methods in particular, one thing we looked at was the map from K-theory to topological Hochschild homology. And so you could ask, well, is there an analog of this in real algebraic K-theory? And this question was considered by Hesselholt and Madsen, and there's also been a lot of work due, for instance, to Emanuele Dotto on this question. And the answer is yes, there is a theory of trace methods for real algebraic K-theory. And in particular, there's a map from real algebraic K-theory to something called real topological Hochschild homology. So I'm going to define that right-hand side. It's not meant to be apparent yet at all what that is. And I'm also going to argue that the right-hand side is an equivariant spectrum, just like THH was S1 equivariant, but now I claim it's going to be equivariant for the orthogonal group. And just a note here that, because it will be relevant momentarily, is that the orthogonal group is the semi-direct product of S1 and C2. And so that's maybe to convince you even now that why you might think that it would be equivariant for the orthogonal group is that THH was S1 equivariant. And now this involution is somehow like incorporating a C2 action into everything. And so I claim that what happens is we get an O2 equivariant spectrum. Okay, so what I want to do is I want to tell you about THR. So the work I want to talk about today is really about real topological Hochschild homology. And so I'm going to have to tell you first what it is. So what is THR? And before I can even define THR for you, I want to think back to our definition of THH or Hochschild homology. We had this cyclic bar construction. So we started by defining a simplicial object. I want to do the same thing here, but I want my simplicial object to somehow incorporate the involution, right? I want to think of this whole theory as like adding in an involution to everything. So there is a way to incorporate involutions into simplicial objects. So these are often called real simplicial objects. And what is a real simplicial object? Well, it's just a simplicial object, so it has all the usual stuff. Plus, it has these maps, these involutions at each level. So at level n, it has a map Wn that squares to the identity. And to be, to think of this as an involution, a simplicial object with an involution, it has to behave a certain way with respect to the face and degeneracy maps. So there are some relations that we ask for real simplicial objects to satisfy. Okay, so if you have a real simplicial object, one thing that's very nice about this is that, again, we know something about the geometric realization. So the geometric realization of a real simplicial object has a Z mod 2 action. Okay, so what I want to do now is I'm trying to define real topological Hochschild homology for you. And we talked about the cyclic bar construction. To define THR, I need another version of that, which is called the dihedral bar construction. So I'm going to tell you what the dihedral bar construction is. So the input for this is one of these ring spectra with anti-involution. So let this A tau be a ring spectrum with anti-involution. And I'm going to define the dihedral bar construction. So this is the definition of the dihedral bar construction, which we usually write B di of A. And what is the dihedral bar construction? Well, it's going to be a real simplicial object. So it's the real simplicial spectrum. And I need to tell you what is it at the qth level. Now, remember in the cyclic bar construction at the qth level, you had like q plus 1 copies of your thing. So here, that's what we're going to have as well. But I'm going to write it in a weird way. I'm going to write it as A smash q copies of A. So that's still just q plus 1 copies of A. I've just made a seemingly strange choice of how to write it. Okay, so if I look at my picture, it looks so far just like what we had with the cyclic bar construction. Level 0, I have A. Level 1, I have 2 copies of A, 3 copies of A, etc. Okay, and actually it looks even more like the cyclic bar construction than that, because the simplicial maps, the face and degeneracy maps, are just the standard ones. They're the ones we defined earlier, the standard ones in the cyclic bar construction. Okay, so exact same definition as earlier for my face and my degeneracy maps. Let me just draw those in. Okay, so my picture is so far looking just like the cyclic bar construction. But it's supposed to be a real simplicial object, right? That was what my definition said. And so a real simplicial object, I have to specify an involution at each level. So I need to tell you at level n of this simplicial object, what is the involution? So I need to have a level-wise involution at the qth level. And my level-wise involution, it does two things. So the first thing, which maybe you would guess, is A has its own involution, right? A is a ring spectrum with an involution. So I can just do the involution on all the copies of A. So I'm going to act on all copies of A by involution. Okay, so that's one thing that it's going to do. But it does something else as well. So in the A smash Q part of that, so up here I like separated out one kind of special copy of A in all the rest of the copies of A. So I have a bunch of, I have a bunch of copies of A smash A, smash A, smash A, smash A. In all the rest of the copies of A, it's going to flip the copies about the center copy. So it's going to flip these two, it's going to flip these two, etc. So in my picture, that would flip these two, would flip these two, it would flip these two and these two. and so on. So except for that first copy, it's flipping all of the copies of A about the sort of center in those remaining Q copies. Okay, so that gives some involution, and you can check that it's real simplicial. So there were some, I'm going to scroll up for 1 second. There were some identities that had to satisfy, and you can check that that does satisfy those identities. And there's one more thing happening here. So in the ordinary cyclic bar construction, there was also a cyclic group acting on each level, and we still have that, right? I can still define the same cyclic operator we had earlier. So the cyclic operator, TQ, from A smash AQ to A smash AQ, same one. So this is going to be which rotates the last factor to the front. Okay, so that gives me now a cyclic group action. I've got C2, C3, C4, C5, trivial group. And this is my dihedral bar construction. So it looks just like the cyclic bar construction with the addition of this information from the involution. Now, it's real simplicial, I claim. And so that means when you realize it, you get a Z mod 2 action. But, you know, in the cyclic bar construction, that was cyclic. And so when you realize that, you got an S1 action. And so a really natural question to ask is like, how do these cyclic group actions interact with this involution action, right? Like, how do those two things interact with one another? So let's ask that. So how do the cyclic action and involution interact? Okay, and you could think about that for a little bit if you sort of write down a couple of them and see like what do you think? Like, do they just commute? What happens? What you'll find is that the following thing happens. If I do my cyclic group action followed by my involution on the qth level of this thing, it's the same thing as doing the involution first, but then it's not TQ, it's TQ inverse. Okay, so this is the relationship that you have between the cyclic group and the involution at each level. And so what does that tell you? It tells you what happens when you try to put these two actions together at each level. So in particular, what it tells you is that at each level Q, we have an action now of, so before we had a cyclic group action, now we have an action of the semi-direct product of the cyclic group and C2. The semi-direct product of a cyclic group and C2 goes by another name. This is AKA, this is a dihedral group. So this is the dihedral group D2Q plus 1. Okay, so what have we said? We have this object, this simplicial object with all this additional structure, and we've learned that at each level it has an action of the dihedral group. We can characterize exactly this kind of object, this kind of real simplicial object with a cyclic action that satisfies this relation. And this is called, so sometimes this is called a real cyclic object. Or you could call it a dihedral object. So either of those names exist in the literature. And what is the takeaway? Well, the takeaway is that when you realize this, we understand what happens. The realization of a dihedral object or a real cyclic object has an action of, well, what happens? So the C2 sort of, we had a C2 action at each level. And so when we realize that, we expect to have a C2 action. The cyclic group actions, they sort of change by level. And just like with the cyclic bar construction, when we realize them, they assemble into an S1 action. And so when we realize this, what do we get? The cyclic groups assemble into an S1 action. And we end up with an S1 semi-direct product C2 action, which is the orthogonal group O2. Okay, so all of that was to say that the dihedral bar construction, it has, upon realization, it has an action of the orthogonal group. And so I was trying to define real topological Hochschild homology for you, and here it is. Real topological Hochschild homology is the realization of the dihedral bar construction. And so in particular, it's an O2 spectrum, has this, this action of the orthogonal group on it. Okay, so I'm finally ready to say, you know, what it is that I really want to talk about in this talk, which is the following question. So, you know, this is like, what was the story in trace methods? The story was we had this algebraic theory of Hochschild homology, which wasn't quite good enough. And so we developed a topological version of it, which was THH. And now I've said in this setting of rings with involution, we have an analog of THH, which is THR. But it leaves open a very natural question, which is, what is the algebraic analog of THR? Right? So in the classical story, THH came from some algebraic theory. There was this classical algebraic theory. And THR didn't come about that way. It came about as a topological theory. But it should have some algebraic analog. And in the setting of THH, knowing about the algebraic analog was really essential to understanding THH. That's how we do calculations with the Hochschild spectral sequence. We can do calculations using the linearization map. And so we really want to know, like, what, like algebraically, what goes here? What is my algebraic analog of THR? Okay, so this is the question I'm after, which is, what is the algebraic analog of real topological Hochschild homology? But to answer this, we need to take a little bit maybe of a, I don't know if detour is the right word, but we need to talk a little bit about norms in equivariant homotopy theory. So I claim that these norms in equivariant homotopy theory, they're going to help us understand the answer to my question. Okay, so what are norms in equivariant homotopy theory? So a few years ago now, Mike Hill, Mike Hopkins, and Doug Ravenel proved this amazing theorem about the Curvaire invariant one problem. So it's a very prominent theorem. But one amazing thing that came out of the Hill-Hopkins-Ravenel work is that they laid the groundwork for huge advances in equivariant homotopy theory. So a lot of what they did in service of proving, you know, the one application they were interested in, laid the foundations for advances kind of across the field. And one reason is because they developed this theory of multiplicative norms in equivariant homotopy theory as part of their work. So what is the Hill-Hopkins-Ravenel norm? I'm not actually going to define it, but what kind of thing is it? It's a functor from an H equivariant spectrum to a G equivariant spectrum, where H is a subgroup of G and they're both finite groups. So it gives you a way to move from H spectra to G spectra. I want to note that they proved a proposition about these norms, and it'll hopefully become clear later why I want to mention this particular proposition. But one thing we know about norms is that in the commutative case, so if you're only interested in commutative H spectra and commutative G spectra, it's left adjoint to the restriction functor, the functor where I just think of my G spectrum as like an H spectrum for the smaller subgroup H instead. So this is one sort of, it's like if we want to check if something is a norm, which maybe we will momentarily, one kind of like reality check is in the commutative case, is it left adjoint to restriction? So that's true for the Hill-Hopkins-Ravenel norm. Okay, so Hill-Hopkins-Ravenel, they make this definition of these equivariant norms, but one limitation of their construction is that their construction of the norm only applied to finite groups. Now, they only needed that for what they were doing, so maybe limitation is the wrong word, but their construction only applied to finite groups. And so you could naturally ask the question, like, can we take norms to groups that aren't finite? Like, what would it look like to take the norm to a group that isn't finite? And so the first one of these constructions of the norm to a non-finite group was a few years ago in some joint work of Wiegleich Engelveit, Andrew Blumberg, myself, Mike Hill, Tyler Lawson, and Mike Mandel. There was related work around the same time of Martin Stoltz. We constructed norms to S1, to the circle group. And we showed that you can define a norm functor from associative ring spectra to S1 spectra. So this is like a norm from the trivial group to S1. And what we showed actually is that the cyclic bar construction is a construction of such a norm. So we showed in this work that the cyclic bar construction is a norm to S1. And if you're bothered by this like curly I in front of it, that's a change of universe functor that I'm just trying to write things that are true, but I don't really want to go into, if that's familiar, great. And if it's not, don't worry about it. But so we describe one of these norms to the circle. Let me mention that there is some very recent work of Andrew Blumberg, Mike Hill, and Mike Mandel, where they are working on a more general theory of norms for compact Lie groups. And so one of the sort of checks that they do for their new theory of norms for non-finite groups is they show that their new definition, which uses equivariant factorization homology, agrees with this definition that we have for S1 in that case. So there is this more general theory that they're working on right now. So what does this say? So in one way of thinking about what this says is that this says that topological Hochschild homology is an equivariant norm, right? It was defined as the cyclic bar construction, which now this work says we should really think of as like the norm from the trivial group to the circle. And in this work, we also look at norms from like cyclic subgroups of S1 to S1 as well, but I'm going to focus just on this trivial group story right now.
Excuse me, Teena.
Yeah.
You don't need to change the universe here.
Yeah, I mean, the change of universe is like, it's having to do with the fact that when you geometrically realize the cyclic bar construction, what did I say? I said it's a cyclic object. So what you get is a spectrum with an S1 action, right? You get a spectrum and it has an S1 action on it. So that's like a very naive notion of what we mean by S1 spectrum, to just say that it has a spectrum with an action. When we talk about equivariant norms, we usually want to work in a more genuine equivariant setting. And so all this change of universe functor is doing there is it's taking like this naive notion of equivariant and it's changing it to a genuine equivariant S1 spectrum. And for THH, we should, depending on what we want to do with THH, we should probably do that as well. So the change of universe, I mean, I didn't put it there when I defined THH, but you could. It depends on what kind of, I mean, you can view THH in all these different ways. Like I could view it as a naive S1 thing. I could view it as a genuine S1 thing. So yeah, so that's, I sort of wrote a more naive thing earlier, but yes, you could have a change of universe functor there as well.
Okay, thank you.
Yeah. Okay, so I want to think about how this works, what this has to say about real topological Hochschild homology. So we've been talking about THR, and I want to try to think about a norm perspective for THR. So remember, for THR, the input should be the same as real algebraic K-theory. So the input is supposed to be a ring spectrum with anti-involution. I'm trying to translate things into equivariant homotopy theory because that's where like these norms are about equivariant objects. And so the note here is that an involution is really a C2 action, right? It gives you an action of the group C2. And so we get a C2 equivariant homotopy type. So these ring spectra with anti-involution, they are, in particular, C2 ring spectra. It's not all C2 ring spectra. There's some particular C2 ring spectra that are these ring spectra with anti-involution. And so one thing that we prove or we show in this joint work of Gabe, Angelini-Knoll, myself, and Mike Hill is that we construct an equivariant norm. We show that if I'm interested in the norm from C2 to O2, so from the cyclic group of order 2 to the orthogonal group, that you can construct a norm using the dihedral bar construction. And so you might ask the question like, how do you know that that's the norm? And I'll give maybe a couple answers to that. But the first answer of why you should believe that this is the norm is that in the commutative case, it does the thing that the norm is supposed to do. This is the functor that's left adjoint to the restriction functor. So that's a good reality check that, yes, this makes sense as a model for the norm, and we'll see some more sort of reality checks later. But so we construct this equivariant norm to the orthogonal group. And that's nice. One reason that that's nice is because, this is another construction of a norm to an infinite group, which, as I said, are only understood in some limited cases, except for this work, this recent work of Blumberg, Hill, Mandel, where they're trying to do this more generally. The takeaway also is that this tells you that THR is an equivariant norm. So THR of A is an equivariant norm. So I can think of real topological Hochschild homology as the norm from C2 to O2 of A. And why is it nice to know that? Like, why, I'm a practical person. Like, I mean, it's kind of abstractly, that's a nice thing to know. But in practice, why is it nice to know that real topological Hochschild homology is an equivariant norm? So why is this nice? Well, one reason that it's nice is that for finite groups, it's well understood how restriction and norms interact. And in our work, we can extend that to this not finite setting. So this is technical, and maybe the exact details of it are not the point, but what we prove here is that if I take the norm from C2 to O2, so that's THR, that's an O2 spectrum. But I could ask, let's just forget that it's an O2 spectrum and just think of it as a spectrum for the dihedral group. So that's a subgroup of O2. And what this formula says is it gives a really concrete description of what does that look like as a spectrum for the dihedral group in terms of these finite norms. Like these are on the right-hand side, these are classical Hill-Hopkins-Ravenel norms of this spectrum. There's some notation. Zeta is a root of unity. The C zeta is like an equivalence of categories you have to use to make things precise. I don't want to dwell on that, but what you should think of this is that we can use this norm characterization. It gives a really nice description of what happened, how to view THR as a spectrum for these subgroups. Well, I just want to mention this extends an earlier result of Dado, Moy, Pachkoria, and Ree. And so their theorem, Dado, Moy, Pachkoria, Ree, their theorem was like a C2 version of this. So they proved that if you look at THR as a C2 spectrum, you get A smash over the norm of the restriction of A with A. So this is, you can convince yourself like this is the D2 version of our D2M result above. So we can extend what was understood for C2 now to all dihedral groups.
Hi, Teena, just a quick question.
Yeah.
So should I think about this like restricting the action theorem as something along the lines of, okay, I took the n-fold subdivision of usual THH, and I could think about that with like the term-wise CN action from the subdivision. And when you realize that, that has a CN action, and that's the same as the restriction of the S1 action on the realization of THH without the subdivision.
Yeah, exactly. So in
Okay.
improving this result, it's like the same kind of thing, like you're saying something about THH, but we have the same kind of result here where what you want to do is you want to like, you're really doing like a subdivision. Now it's going to be a dihedral subdivision. So there's a dihedral notion of subdivision, which like combines the Bogstad-Chang-Madsen subdivision and Siegel subdivision in some creative way. There's a dihedral subdivision, and that's the model that of the left-hand side that you end up comparing with the thing on the right. But yeah, exactly.
Awesome.
That kind of idea.
Thank you.
Okay, so this perspective, I was really after this algebraic analog, and I claim that this perspective helps us somehow with our algebraic analog. So how do we see that? So classically, we had this linearization map, and with the real analog, I'm trying to figure out what is the algebraic analog of THR? If I do linearization, what does it map to? Okay, and to understand that, it's here it mapped to, oops, wrong button. It mapped to something about pi naught of R in the classical case. And so the first question is what kind of thing is pi naught of A? I have this A, and what kind of thing is pi naught of A? What should be the input of my algebraic theory? Well, to try to understand what kind of thing pi naught of A is, let's just remember a little bit about equivariant algebra. So when I say equivariant algebra, I think of this as the algebra that arises in equivariant homotopy theory. And when I talk about equivariant algebra, I'm always letting G be a finite group. I shut the door, sorry. Okay, so probably familiar, but let me just remind in case it's not, that if we have a group G, we can define a Mackey functor for G. So what is a Mackey functor? It's really a pair of functors, M lower star and M upper star. One of them is covariant and one of them is contravariant. They're functors from finite G sets to abelian groups. And we ask for a few things. One of them is that they have to evaluate to the same thing for each finite G set. So their values have to agree. And I give that a name. I call that M underline of X. These functors have to be additive in the sense that they take disjoint union to direct sum. And then I'm just gonna cheat and say plus axioms. So they have to satisfy some nice axioms. And so what are these Mackey functors? So what we should think about Mackey functors, if we're not familiar, is the following slogan. So Mackey functors are the abelian groups of equivariant homotopy theory. Okay, that's selling Mackey functors a little bit short because Mackey functors have lots of applications to things that are not equivariant homotopy theory. But in the context of what we're talking about today, Mackey functors are the abelian groups of equivariant homotopy theory. What do I mean by that? I mean, in ordinary homotopy theory, we have a lot of invariants that give abelian groups. In the equivariant world, you expect your invariants to spit out a Mackey functor, not an abelian group. So an example to illustrate that principle is if we think about what happens when you take the homotopy of an equivariant spectrum. So if I take the homotopy groups of an ordinary spectrum, I get an abelian group. For an equivariant spectrum, when you take the nth homotopy, you get a homotopy Mackey functor, not a group. And so the Mackey functor, I have to tell you what it evaluates to at each orbit. And I feed it the G set, G mod H, and I get the homotopy groups of the fixed points. Okay, so these Mackey functors, they have a couple of nice things that I want to mention about them. With abelian groups in ordinary homotopy theory, you can associate an Eilenberg-MacLane spectrum to them, so you can get a spectrum from them. With Mackey functors, you can similarly get an Eilenberg-MacLane spectrum, but now it's an equivariant spectrum. It's characterized again by the homotopy being concentrated in degree 0. The category of G Mackey functors has a symmetric monoidal product, which is called the box product. So if I have two Mackey functors for G, I can take their box product. This can be defined in a very algebraic way. I don't know if cheat is the right word, but I'm going to give a very topological definition of this. This is maybe not the most classical definition of the box product, but here's one way of saying what it is. I could take the Eilenberg-MacLane spectrum of M, the Eilenberg-MacLane spectrum of N, and I could smash those together. That's a G spectrum. I wanted a Mackey functor, so I could take pi 0. So this agrees with more algebraic characterizations of the box product. And then I can look at monoids in that category. So like monoids under the box product, they're called green functors. So these are like the rings of equivariant algebra. Okay, so we have this translation between equivariant topology and equivariant algebra, where I said if you have a G spectrum and you take pi 0, you get one of these G Mackey functors. If you feed it a G ring spectrum and you take pi 0, you get a G green functor. But I want to feed things a ring spectrum with anti-involution. That's what I'm interested in for THR. And what you get is a special kind of Mackey functor called a Hermitian Mackey functor. So that term was coined by Dotto and Ogle. I'm not going to define it because it's technical, like what makes it a Hermitian Mackey functor, but you should just think it's like the analog of a ring spectrum with anti-involution in this equivariant algebraic world. Okay, so what does it mean? What are we looking for? I guess what I'm looking for when I talk about my algebraic analog of THR is I want it to take as input a Hermitian Mackey functor. And so I want some theory of real Hochschild homology. This is what I'm after, is some theory of real Hochschild homology that will take as input one of these Hermitian Mackey functors. Okay, there's one missing piece before I can tell you what the definition is. So the last missing piece comes from some work of Hill and Hopkins. In the spectra setting, I needed these norms of spectra, and it turns out in the Mackey functor setting, I need them as well. So I need to know how to take a norm of a Mackey functor. So let H be a subgroup of G, and for M, an H Mackey functor. Hill and Hopkins defined the norm from H to G. So they defined, if you feed this an H Mackey functor, it's going to spit out a G Mackey functor. And here's their definition. I could take the Eilenberg-MacLane spectrum of M. That's an H spectrum. I could take the norm in spectra from H to G. That's a G spectrum. And I could take pi naught of that to get a G Mackey functor. Now, this is a very topological characterization of the norm, and several people have written nice algebraic characterizations as well. Like there's work of Kristen Mazur and Rolf Hoyer on this. So you don't need to go through topology, but this is the most simple one to state. Okay, and so finally, I'm ready to tell you what real Hochschild homology is. So at the bottom of this slide, I'm just recalling our norm perspective on THH gave us this double coset formula. So this was the same formula that we had earlier. Using this formula and this notion of norms for Mackey functors, we can define the real Hochschild homology of a Hermitian Mackey functor. And here's the definition. It's the homology of a two-sided bar construction that involves these Mackey functor norms. And if you compare this line and the line above, you can kind of see why you might believe that this is the right thing to be compared to THR. And we prove, so our claim is that this is the algebraic analog of THR. This is that missing algebraic analog. So this is the algebraic analog of THR. And if I want you to believe that, I should justify it. So let me give you a justification. Here's one. It's related to THR via a linearization map. So I have a linearization map that relates real topological Hochschild homology to real Hochschild homology. And linearization is an isomorphism in degree 0. So that was one of my desired properties from an algebraic analog. The other thing is, you know, in the classical setting, Hochschild homology and topological Hochschild homology, they were related via a spectral sequence, and that spectral sequence was really useful if I wanted to compute THH. So you could ask, is there a version of that spectral sequence that relates real Hochschild homology and topological Hochschild homology? And there is. It's a theorem of Chloe Lewis, who's one of my PhD students. she proved that there is a real Hochschild spectral sequence, and the story is beautiful. It's just what you would want. It has E2-term real Hochschild homology, computes the equivariant homology of THR, and she's used that to do some nice calculations of THR. And then over time, so let me just close by saying that that this kind of approach through real Hochschild homology is also computationally useful for THR. So in the work with Gabe Angelini-Knoll and Mike Hill, we, for instance, compute pi0 of THR of HZ. So that's that Z underline is the constant Mackey functor for Z. And we give this characterization on the right, which is that's a quotient of a Burnside Mackey functor. And so the details are less important, but I just want to argue that because real Hochschild homology is purely algebraic, you can use homological algebra tools for Mackey functors, and you can do explicit calculations at the level of pi0, where you know that you have this isomorphism. Okay, I apologize for going a little bit over time. I am done. I'll stop there.
Yeah, let's thank Teena for a beautiful talk. Any questions?
Hi, I have a question. So in the, how do I say? So there's more structure that a ring can have in equivariant homotopy here. Like it could be ring or it could have a Tambara structure. Is there some potential interaction with like a Tambara ring structure with this real equivariant version of the Hochschild homology?
So are you asking, like, if you feed this thing a Tambara functor, does it give you anything?
Anything special?
Extra?
Yes.
I guess my answer is sort of, I'm not sure, but I guess my one thing I could say is that, so part of the project that I haven't talked about in this talk is like, this also gives you a way of talking about, like Witt vectors for rings with anti-involution. It's kind of similar to like the stuff about Witt vectors for green functors, where it's like you can use this HR0 as kind of a characterization of a theory of Witt vectors. And then you do want things to be Tambara functors in order to have things work out nicely. But I don't know, I don't have a good answer for like whether the Tambara functors in the sort of more general sense give you extra things that are nice. I'm not sure.
Thank you.
Other questions?
Could I ask, please? Hello, very nice talk. I'm Peter Webb. And so the like one thing you had was a definition which I'm not familiar with due to Hill and Hopkins. If you've got a finite subgroup H and you've got a Mackey functor for H, then you have a norm of it, which is a Mackey functor for G. And so what you put down may be the same thing as what I'm about to say. I'm not sure. If you've got a Mackey functor for H and you want to get a Mackey functor for G, you could take G sets and you could restrict them to the subgroup H, and then you could evaluate your Mackey functor for H on that restriction of a G set, and you would get now an expression defined on G sets. So you would compose first the restriction of G sets. How does that relate to the construction which you're referring to here?
Yeah, it's not the same. So this is like, right. So that's not the same as this norm construction for Mackey functors. And in fact, if you try to write down, so the one reason I gave this characterization is that if you try to write down explicitly, like what is this multiplicative norm for Mackey functors, it's quite complicated to articulate what this should be. So there are some, so Kristen Mazur, for instance, does this for if G is a cyclic group. She writes down like real explicit formulas, which end up being like in terms of you have to quotient by Tambara reciprocity relations and all kinds of things. And so, so it's not the same as what you're saying. I don't know what the best thing is to say about the relationship between those two characterizations. I guess what I'll say is that like Hill and Hopkins in this work, they were trying to understand like, how do you characterize like genuine commutative structures in equivariant homotopy theory. And so they were trying to define like what that really means. And it turns out that like these kinds of norms arise in that work of understanding like sort of genuine commutative structures that arise in equivariant homotopy theory. So they were looking for like norms satisfying, a multiplicative norm that satisfies sort of particular I don't know, relations with respect to what their goals were. So I'm sorry, I'm explaining this poorly,
So,
but it's more complicated than just the restricting. It's a much more like subtle construction.
There is a tensor induction for Mackey functors, which has been defined by Book, for instance, and he has worked on that. Is this the tensor induction?
No, I don't think so.
Okay, so it's different again. I have to say I find it hard to imagine what it could be then, but I must have a look at it.
Yeah, I mean, so this is like a very topological characterization, but for a more algebraic description, there's work of Kristen Mazur, who does this when like she's focused on cyclic groups. And so she constructs like really explicitly with formulas, like what this is. And so she would do this in her thesis. I think the actual like published version is joint with Mike Hill. So Hill, Mazur. And then Rolf Hoyer, also in his thesis, he gave characterizations of this as well that don't go through topology. So this is like the Hill-Hopkins approach is very good if you want to prove theorems about this. It's like, I don't know, it captures what is the relationship between the topology, but if you want to actually calculate it, you don't want to use the Hill-Hopkins definition, you want to use these other characterizations. So Rolf Hoyer also worked on this. I think that his work is unpublished though, so this was like his thesis, and if you Google Rolf Hoyer thesis, you can find it, but he gave sort of formula descriptions of this as well. But yeah, so those are some places, but Kristen Mazur, especially in her thesis version, has some nice sort of motivation for what kind of thing you're looking for when you define these norms for Mackey functors. But it's really about capturing like what happens in the equivariant stable homotopy theory.
Yeah, I mean, I must have a look at that. I think I did have a look at her paper actually, but I can't remember. And I was looking at somebody's work where they were doing these calculations for cyclic groups, and it might very well have been that. There can't be many possibilities, but they also in terms of the definition of what this thing is. I mean, my reaction is there are only so many things you can do with G sets. Like this is finite groups, and we're talking about actual Mackey functors, and it can't be that bad. I must think about it and see what it is. There was another place in your talk where you mentioned in your context that such and such was a left adjoint of a restriction. And I have to say, I can't actually think of a circumstance where you're dealing with finite groups that I have encountered where the left adjoint of restriction is not, when you're going down through finite index, is not also the right adjoint. Is this a situation where the right adjoint is not the same as the left adjoint, where you've got finite groups, finite index?
Yeah.
So it's that you know it to be different, do you?
I believe so.
Yes.
Yeah, I was gonna say.
Okay.
Yeah.
Okay. I must look at that as well. Very good. Thank you.
Yeah.
Hi, Teena. I had a question about this Hochschild spectral sequence that Chloe has constructed.
Yeah.
Is there any sort of real analog of the, celebrated, Hochschild calculation of THH of HFP, and sort of like that result is kind of really integral to a lot of different kinds of things you might want to do with THH. Like, is there a result along these lines, and are people thinking about how they could apply this? Of course, things are very different in equivariant algebra land, so I have no idea what to expect.
Yeah, I mean, the answer, I guess, to your question is no, not yet. Okay, so she is able to do calculations with her spectral sequence, but I guess the sort of but is that the E2 term here is much harder to compute than ordinary Hochschild homology. And so things are, yeah, it's less approachable than in the non-equivariant setting. And I think your question is great, right? It's like you would like to have some analog of this Hochschild result, but it's not so easy even to compute like the E2 term in that kind of case. And so she hasn't done calculations like that quite yet. There's also like, as you can imagine, in the ordinary Hochschild spectral sequence, and the way I stated it earlier, it's like you always take coefficients in a field, right? You take homology with field coefficients. And why do you do that? You do that because you, like, in the construction of the spectral sequence, that allows you to avoid adding a lot of flatness hypotheses to your spectral sequence, right? When we work in this equivariant algebra setting, it's like inherently we pick up flatness hypotheses. I don't want to go into exactly what they are, but you pick up some flatness hypotheses along the way. And so you have to make sure that you're in a situation then where you're like working with a homology theory such that your flatness hypotheses are going to be satisfied for the examples that you're working with. So there are extra like layers of complexity that come in, but I think your question is a good one. And I think it's very interesting to think about. We have sort of analogous spectral sequences like this for twisted THH as well. And so there too, it's like, it would be nice to understand what those say about, like, for instance, the twisted THH of HF2.
Yeah.
Turns out that's pretty hard to do with a spectral sequence. So
yeah, is there hope to kind of get at that sort of thing with some kind of equivariant Tom construction? You can sort of use this,
right,
like,
yeah.
yeah.
I was going to say that. So I have a different project, but I have a paper with Catherine, I can't do it alphabetically, but let me just say these. Catherine Adamic and Inbar Klang and Catherine Hess and Hannah Giacong, and where
Awesome.
we look at like this equivariant spectral sequence for twisted THH. And there, with Inbar on the team, Inbar was like, maybe, same comment, maybe equivariant Tom spectra are better here. So we do a calculation of like twisted THH for HF2 using an equivariant Tom spectra approach instead,
Awesome.
Which is much more, as you're saying, much more suitable in that example. And I think Inbar has work where she's thought about that kind of thing for THR as well. I'm a little bit less familiar with that, but I think that she's thought about, what can, if you think about the like Blumberg, I'm having a mind blank, but Ando, Schlick rule, whatever, the stuff about THH and Tom spectra in the classical setting, she's thought about like, what does that say for THR, and done some calculations there as well.
Awesome. And just one more quick question, if there's time. So for like the analog of TRR that you might want to write down, do you just do the genuine fixed points with respect to the dihedral groups, like instead of and you sort of like, what does that look like? Because I know how to do it for TR with just like the cyclic groups and the divisibility poset, but
so there's like a whole theory of like what you're getting at of like TCR, like I didn't talk about that, but there's like real topological cyclic homology as well, and like TRR, and for instance, Emmanuel Aidato and collaborators have written a lot about that, and so you can define those things like TRR, you can define those by taking genuine fixed points, as you're saying, but you could also ask like, lately we like to like Nikolaus-Schulze everything and like not take the genuine fixed points. And so you could ask like, can we get away with a more like modern cyclotomic approach? And there's work of Quigley-Shaw where they talk about like, how do you think about TCR using like an analog of the Nikolaus-Schulze approach in this setting. So people have developed both theories of TCR from like a classical Bakshad-Chang-Madsen approach and from a Nikolaus-Schulze approach. But one piece that's missing, or I guess I'm not totally sure, it hasn't appeared yet. It's supposed to appear. I don't know. People say that they've, anyway, I'm not being skeptical that they've done it. It just hasn't appeared yet. Anyway, no judgment. But it hasn't appeared yet that the trace map actually from KR to TCR.
okay,
so there's like constructions of TCR, but we don't have like you know, the thing that makes trace methods go is like the Dundas Goodwillie McCarthy theorems about this, and the Bogstad Zhang-Madsen trace and stuff, and that stuff isn't yet in the literature for real algebraic K theory.
Interesting. Cool. That's good to know. Right, I'll shut up. I could just bug you with questions for a while.
Yeah, sure.
Thank you, Teena.
Yeah.
It looks like the seminar naturally moved into discussion after the seminar, which is great. Yeah, so, but I want to ask a question.
Yeah.
Since Hochschild homology corresponds to free loop spaces, what is what does real Hochschild homology correspond to in this way?
Yeah, it's a great question. I don't really know how to think about real Hochschild homology through that kind of lens, or even. Yeah, I don't know. I'm not sure. That's a very interesting question, but I'm not sure what we can say about like how to think about these more like dihedral constructions.
Right. Yeah, you can start with a space or a spectrum with an involution, and then move on to and then consider the corresponding, like, I don't know, co-chain complex, and apply the Hochschild. Try to apply the real Hochschild homology to it and see what you get.
Yeah.
Or you start with something which doesn't have, for which the involution is trivial, but then still at the level of a real Hochschild homology, topological real Hochschild homology, or a real Hochschild homology in the algebraic case, you will get some something non-trivial, I guess. Right? What
Yeah, I don't. Yeah, it's a good question. I haven't thought. Right. Yeah. Right. There should be some kind of like. Yeah, I'm not sure. No, it's a good question. I just haven't thought about any kind of like geometric interpretations of of what we're getting. But yeah, I don't know. It's
yeah. Interesting. Well, how many people are left? It seems like Peter is left and myself. Right. Yeah, Peter, if you want to continue the discussion, you're welcome to do it if Teena has time.
I'm good. Thank you very much. I wasn't you know, we don't know each other, I think. And when at the beginning of your talk, I thought it was I didn't know what to expect, and then you started talking about Mackey functors at some point, which is something I'm very much interested in.
Yes.
The algebraic point of view, so I'm very glad to hear these things that you have to say, because the topological connection is not something that I have focused on at all. And probably the main people who are doing Mackey functors these days are topologists.
yeah.
Actually, which from my perspective is great, because like I've had something to do with the development of the theory of Mackey functors, but it's always seemed so abstract. And you wonder, what's the point? Is anybody going to be interested in this? You know, and then I know there are quite a few people actually who are using these things. It's just great. So thank you for your talk.
Thank you for having me.
It's a great talk. I'm turning off